First, let's meet our team members. Hello geeks, this is our video about distributed systems. In this video I'll try to provide a concise overview about distributed systems and distributed computing. Let's dive into the topic. First, let's explain and clarify what a distributed system is. But before that, let me tell you something that you may not be aware of. Nearly all the software we use today is an extent distributed or involve distributed computing, but how? You're gonna know the answer in a bit from now. Let me just give you some examples to prove that. Distributed systems and distributed computing are all around us. Google search engine, Amazon platforms, Netflix blockchain, online gaming, money transfer and online banking. And the list goes on. Probably the most straightforward and the simplest example of distributed systems is the client-server model, which I assume you are already familiar with, and we will explain more about it later in the video. Now let's go back to the fundamental question and see what exactly a distributed system is. A distributed system is a collection of separate and independent software or hardware components called nodes that are linked together by means of a network and work together coherently by coordinating and communicating through a message passing or events to fulfill one and goal. Nodes of the system could be unstructured or highly structured, depending on the system requirements. A distributed system is a collection of computing elements, each being able to behave independently of each other. A computing element, which we will generally refer to as a node, either a hardware device or a software process. A second element is users. Distributed hardware cannot use a shared memory due to being physically separated, so the participating computers exchange messages and data over a network. This inter-machine communication occurs locally over an intranet or across the country and world via the Internet. Messages are transferred using Internet protocols such as TCP/IP and UDP. The complexities of the system are hidden to the end user, making the whole system appear as a single computer to its users. So basically it's just a bunch of independent computers that cooperate to solve a problem together. In line with the principle of transparency, distributed computing strives to present itself externally as a functional unit and to simplify the use of technology as much as possible. For example, users searching for a product in the database of an online shop perceive the shopping experience as a single process and do not have to deal with the modular system architecture being used. Let's see how distributed systems work. To make it easier, we are going to take an example of web application that is experiencing twice as much workload as just a month ago. Of course the performance would be affected. Users will also notice. So the first thing that comes to your mind is to upgrade the hardware, add more memory and bandwidth and so on. But at a certain point it would become technically and financially impractical to upgrade the system. That's where distributed computing can help users meet their increasing demands. Information is read a lot more frequently than inserted or modified in a typical web app. Distributed computing allows using multiple configurations of computers, including master-slave replication, which helps increase read performance. In our example, we can create new database servers that will act as a slave to sync with the primary server, which is the master here. The database servers are only meant to read information. Whenever a user tries to access or read information, the two new servers handle the request, while the master server handles insert and modification requests. The master server keeps the slave servers updated about the new changes and entries. There's a lot of functions that distributed computing does, but we are going to talk about the most important of them. First is resource sharing, whether it's the hardware, software or data that can be shared. Second is openness. It's how open is the software designed to be developed and shared with each other. Another function is concurrency. Multiple machines can process the same function at the same time. Scalability is another function, and it's how do the computing and processing capabilities multiply when extended to many machines. Another one is fault tolerance, which is how easy and quickly can failures in parts of the system be detected and recovered. The last function we are going to talk about is transparency, and it's how much access does one node have to locate and communicate with other nodes in the system. Distributed computing is commonly divided into three subfields: cloud computing, grid computing, cluster computing. Cloud providers usually offer their resources through hosted services that can be used over the Internet. Let's talk about some service models examples. Software as a Service SaaS. In the case of SaaS, the customer uses the cloud provider's applications and associated infrastructure. Platform as a Service PaaS. In the case of PaaS, a cloud-based environment is provided to retain control over the applications provided and configure customized user settings, while the technical infrastructure for distributed computing is handled by the cloud provider. Infrastructure as a Service IaaS. In the case of IaaS, the cloud provider supplies a technical infrastructure which users can access via public or private networks. Based on the idea of a supercomputer with enormous computing power, grid computing can access resources in a very flexible manner when performing tasks. Normally, participants will allocate specific resources to an entire project at night when the technical infrastructure tends to be less heavily used. One advantage of this is that highly powerful systems can be quickly used and the computing power can be scaled as needed. There is no need to replace or upgrade an expensive supercomputer with another pricey one to improve performance. Grid computing is specialized in solving problems that are particularly computationally intensive, as it can create a virtual supercomputer from a cluster of loosely interconnected computers. Cluster computing cannot be clearly differentiated from cloud and grid computing. It is a more general approach and refers to all the ways in which individual computers and their computing power can be combined together in clusters. Examples of this include server clusters, clusters in big data and in cloud environments, database clusters, and application clusters. Computer networks are also increasingly being used in high-performance computing, which can solve particularly demanding computing problems. Distributed computing can also be defined by looking at the system architectures and interaction models of a distributed infrastructure. The following are some of the more commonly used architecture models in distributed computing: client-server model, peer-to-peer model, multi-layered model, multi-tier architectures, service-oriented architecture, SOA. Now we are going to talk about each one briefly. In the client-server model, a server receives a request from a client, performs the necessary processing procedures, and sends back a response. Peer-to-peer architecture organizes interaction and communication in distributed computing in a decentralized manner. All computers, which also referred to as nodes, have the same rights and perform the same tasks and functions in the network. One of the examples on the peer-to-peer model is blockchains. When designing a multi-layered architecture, individual components of a software system are distributed across multiple layers, or tiers, thus increasing the efficiency and flexibility offered by distributed computing. This system architecture can be designed as 2-tier, 3-tier or n-tier architecture depending on its intended use, and is often found in web applications. Service-oriented architecture, SOA, is a style of software design where services are provided to the other components by application components, through a communication protocol over a network. Its principles are independent of vendors and other technologies. In service-oriented architecture, a number of services communicate with each other, in one of two ways, through passing data or through two or more services coordinating an activity. It focuses on services and is geared towards addressing the individual needs and processes of company. This allows individual services to be combined into a bespoke business process. For example, an SOA can cover the entire process of ordering online, which involves the following services: taking the order, credit checks, and sending the invoice. Distributed computing makes all computers in the cluster work together as if they were one computer. While there is some complexity in this multi-computer model, there are greater benefits around so. First, scalability. Distributed computing clusters are easy to scale through a scale-out architecture, in which higher loads can be handled by simply adding new hardware. Second is performance. Through parallelism, in which each computer in the cluster simultaneously handles a subset of an overall task, the cluster can achieve high levels of performance through a divide-and-conquer approach. Third, resilience. Distributed computing clusters typically copy or replicate data across all computer servers to ensure there is no single point of failure. Should a computer fail, copies of the data on that computer are stored elsewhere so that no data is lost. Fourth, cost-effectiveness. Distributed computing typically leverages low-cost, commodity hardware, making initial deployments as well as cluster expansions very economical. Distributed computing has become an essential basic technology involved in the digitalization of life. All the internet services wouldn't be there without client-server architectures. Every Google search, Google Maps, Google Earth are leverage distributed computing for their services. Also e-learning, which we used widely during the pandemic. And it's widely used in commerce. Purchases and orders made in online shops are usually carried out by distributed systems. And it's used in meteorology. Sensor and monitoring systems rely on the computing power of distributed systems to forecast natural disasters. Also, many digital applications today are based on distributed databases. Since our specialization is medical engineering, we are going to talk in detail about distributed system medical applications. Distributed system is very important in healthcare aids, mainly in achieving interoperability. Interoperability is the ability of two or more components, applications, or systems to exchange and use information. But what is the importance of interoperability? It's very important for health professionals. It improves access to health record data and health information anytime, anywhere. And it's important also for patients, Quality and safety of care is improved by improving data exchange, quality of data flow, and access of patients' information by health professionals. Health managers also benefit from interoperability as data collection is improved and statistical and economic analysis is facilitated. Even health researchers benefit as availability of medical data is increased, which facilitate the finding of information for their researches. Distributed systems have a great importance in handling distributed patient records. But how? In distributed database architecture, the data is not stored entirely at a single physical location, but instead it is spread across a network of computers and connected via communication links. Distributed database allows faster local queries and can reduce network traffic. Distributed healthcare is the concept of providing decentralized care services, like monitoring vital signs and diagnostic tests, and moving these services closer to the person in need. This helps a healthcare system to keep people in their own homes, by providing the right care and support at the right time. But what makes distributed healthcare very important? With the rising cost of providing healthcare in hospitals, we are starting to see a shift back to home-based care. As hospitals struggle to keep up with the overflow of patients every week, the solution lies in the question: what can we do to keep patients out of hospital? Simply by moving services into a person's home. And by the help of distributed healthcare, it's much easier, as distributed healthcare has the potential to improve quality, reduce costs, and enhance the experience for the person receiving the care. We already have seen how great is distributed systems, but of course it will develop more and more in the future. Let's talk about some points that is expected to be developed in these systems. First, simplicity. Distributed systems will largely disappear from a programmer's perspective, as languages and core APIs are designed with distributed systems in mind. Specifically, with the limitations imposed by a distributed system in mind. Once the common APIs that developers build against are distributed in their design, the applications using those APIs will no longer need to be explicitly distribution aware, which will simplify application code. Second, self-managing. Modern distributed systems cannot be managed by humans. Back in the early 2000s, executives at Amazon and at Salesforce, they had already reached a point at which they could not track and manage things by normal human means. You manage one server much differently than you manage 10 servers, and 10 much differently than you manage 100, and so on. Amazon has between 100,000 and 1 million servers in EC2 now. Distributed systems must be built to self-manage, self-organize, self-heal, and to be fault-tolerant of other parts of the distributed system that have failed. Third, it should be observable. Distributed systems must provide quality information about the distributed system itself. This information is what enables autonomic behavior and diagnosis when things go wrong. Making distributed systems observable is incredibly complex work, because when you most need that information is when things are going wrong. And when things are going wrong is when the observability is almost always completely wrecked. The last feature is self-upgrading. Distributed systems are often part of complex, interdependent systems, in which the distributed system must not go down. Distributed systems need to be hot upgradable, hot patchable, and rollbackable when an upgrade fails. Thank you for your attention. It's finally the end of the video.